Hey, welcome back. Today, we are going to get our hands dirty. Well, figuratively, of course. We're going to take a simple flat piece of sheet metal and using some really fundamental workshop techniques, we're going to bend it, shape it, and join it for good. So let's dive right in. It really can seem like a bit of industrial magic, can it? You start with something totally flat, kind of flimsy, and you end up with a solid, structured object. But how? How does that transformation actually happen? That's the big question we're going to tackle today, and we're going to use these detailed workshop notes as our guide. And this is what we're aiming for. This strong, clean, interlocking seam right here is our end goal. By the time we're done, you're going to understand every single step that went into making this thing, from the very first measurement to that final permanent bond. Okay, so our journey starts with what I like to call the art of bending. See, before we can join anything together, we have to give the metal its shape, its purpose. This is the first crucial step where a boring, flat sheet starts to become something three-dimensional. Every great project starts with a plan, right? And in metalwork, that plan has to be precise. We're starting with an 80 by 100 millimeter sheet, which we then cut perfectly in half. Then come two super important markings, a 6 millimeter line on the front and a 14 millimeter line on the back. And trust me, these aren't just random numbers, they are the exact guides for the bends that are going to create our perfect seam. So let's see how those markings actually turn into action. Over on the left, you've got the schematic, the game plan. And on the right, the written instructions. The whole process is really precise. First, we use that 6 millimeter line as our guide to make a sharp 90-degree bend. Then, we flip the piece over, and on that 14 millimeter line, we create a 45-degree bend. It's this combo, a sharp right angle and a wider angled fold, that creates the perfect little hook and slot for our two pieces to fit together. And now for the final touch, which is honestly more about feel than pure measurement. The two bent pieces are designed to just slot right into each other, but they need a little persuasion. A few careful taps with a hammer, and we close that gap down to just 2 millimeters. This gives us that perfect, snug, interlocking fit that's going to be absolutely essential for a strong weld. All right, we've successfully shaped our metal. So how do we make that connection permanent? Well, now we shift gears from the art of bending to the science of joining, and we're going to use a technique called resistance spot welding. The key to understanding this whole technique comes down to one concept, the plastic point. Now, unlike a lot of other welding methods that actually melt metal into a liquid, spot welding only heats it up just enough to become red hot and malleable, almost like clay, but it's still solid. This is what lets us fuse two pieces together with incredible precision and control. It's pretty cool. And this chart here just illustrates that difference perfectly. Arc welding, which is what most of us picture when we think welding, melts the metal completely. It's super versatile, but it also creates fumes and sparks. Resistant spot welding, on the other hand, because it only heats to that plastic point, is way safer. No byproducts. The trade-off, as you can see, is that it's really specialized for what we call lap joints, which is just where one piece of metal overlaps another. And just like with bending, prep is everything. We start with two fresh 40 millimeter strips. They get hammered perfectly flat, then sanded down to get rid of any oils or gunk that could mess up the weld. We mark a 15 millimeter overlap, and then the whole assembly gets carefully placed between the welder's copper electrodes, all set for fusion. And here is the sequence itself. Think of it like a very precise little dance. Step 1, press and, this is critical, hold the foot lever. Step 2, power on. Now, you watch very, very closely for a little black ring to appear on the metal. That's your signal. That's the visual cue that you've hit the plastic point and you've got a good fusion. The instant you see it, you flip the power off. Only then do you let up on the lever. A quick dip in water to cool it down, and that bond is permanent. Okay, it goes without saying that working with this much heat and electricity requires some serious respect and a laser focus on safety. So let's run through a few critical, absolutely non-negotiable rules, pulled straight from the workshop notes. All right, this first one is, well, it's unique, and you're definitely going to remember it. The notes are incredibly clear here. The metal is considered septic, meaning it can carry bacteria. So if you get a cut, this direct warning and, common sense says get proper first aid immediately. Let's just all agree to follow the instructions on this one, shall we? This one's a lot more straightforward, but it is no less important. We just used a massive electrical current to make this metal red hot. It's going to stay dangerously hot for a while. So always, always use tongs or pliers for handling, never your bare hands. Hey, remember that little black ring we were watching for? This is why that's so important. If you hesitate and you leave that power on for even a split second too long, you're gonna blow right past the plastic point and straight into the melting point. And the result isn't a weld, it's a hole right through your piece. Timing is absolutely everything here. This might be the single most important rule of the entire procedure. That foot lever provides the physical pressure you need to fuse the metal. If you let up on that pressure while the electrical current is still flowing, you're going to get a shower of sparks and a totally failed weld. You have to hold that lever down until after the power is off. And a final, simple rule of workshop safety. The welding tool itself is electrical. It must always be placed on its insulated rest, never, ever directly on the conductive metal table. It's just a simple habit that prevents a whole bunch of potential electrical hazards. So let's just step back and take a look at what we've actually accomplished here. We followed the process from a simple sketch in a notebook all the way to a finished, tangible object. We've built something. Just think about the core principles you now get. You know how to shape metal with precise, planned bends, and you know how to join it permanently by heating it to its plastic point. That's a really powerful combination of physical force and applied electrical science. And that really brings us to our final thought. We focused on the how of one small project, but these basic techniques are the building blocks for so much of the world around us, from car bodies to computer cases. So now that you understand the principles, what would you build?